Hi, we are going to introduce you about quantum computing. To understand quantum computers, you have to understand the basic concept of qubit. In classical computing, the most basic unit of information is a bit. A bit can have a value of either 1 or 0. We can say it is either on or off. A bit can be stored in the memory as an electrical signal that has very different voltages. Quantum computers use quantum bits. In short, qubits. The difference between a qubit and a bit is that a qubit has an intermediate state called a superposition. The value of a qubit can be both 1 and 0 at the same time. An example of superposition can be found in an electron. An electron can have one of two spins, up or down. But the spin of an electron is not determined until it is measured. So, before measurement, the electron spin is in superposition. However, after measurement, the spin collapses into a single state. Each qubit has distinct probability of having the outcome. A qubit can be described as the equation above. Alpha and beta each represents the probability amplitudes of 0 and 1. The probability of outcome can be obtained by the square of alpha and beta. Since they are probabilities, the sum of alpha square and beta square should be 1. Qubits have another interesting feature that is distinguished from classical bits, called quantum entanglement. Entangled means that two things are bound to each other. Suppose two qubits are entangled. The probability of each outcome is 50% each. The values which the first qubit can have are shown in red, and the values the second qubit can have are shown in blue. Because of the probabilistic nature of qubits, we don't know which value the first qubit would have. But after measurement, let's say the value of the first qubit was 0. Then the second qubit must have the value of 0, and we know the value without measuring. The same principle applies for different probabilities, or different sets of entangled qubits. Even though quantum computers does not compute in classical ways, it should make classical 1 or 0 outputs. Because the value itself is probabilistic, the programmer has to consider randomness as a part of the program.
In computing science, algorithm definition is a sequence of instructions to solve the problem. An algorithm to solve it in shorter time and use less memory is the better algorithm in computer. Quantum computer innovatively improves the algorithm with qubit. Each qubit has both possibility of 0 and 1. For example, 3 qubits can choose 8k 2 to the power of 3, but 3 qubits choose 8 possibilities in same time. Therefore, operation with qubit is much faster than conventional operation. The measure of how fast an algorithm is time complexity. It can be described by big O notation. If you have an algorithm to find a number in n number, algorithm's operation time is increased with n. Big O notation shows the relation with entered number n and the operation over time. RSA encryption is the third and most widely used public key cryptography. The key of RSA is integer factorization of large numbers is very difficult. RSA uses a product of two large prime numbers, so the others should do integer factorization to decrypt it. On classical, the time complex is too difficult to solve it with large n in proper time. However, on quantum, the time complexity is followed by Shor's algorithm, and it means classical cryptography can be broken. Quantum Fourier transform is the key of Shor's algorithm. Fourier transform changes the wave to the other wave has different frequencies. In quantum, you can describe each superposition of qubits like a wave. So we can also transform the possibility in quantum computer by quantum Fourier transform. It includes that as the qubit superposition. In the other words, compared to the numbers can be calculated quantum computer at once. In your algorithm, you can think prime factorization to find the order small I defined by Pot formula. A is any number smaller than n and coprime is n. Pot formula and second is the same. Then, if we can find R, greatest common divisor between n and left side of second formula is factor of n. So we should calculate only the new smaller numbered factor. Classical computer can't do it because of R calculation is impossibly much, but quantum computer can do that.
The idea to build quantum computers in order to simulate physics in quantum basis was originally proposed by Feynman. A quantum computer operates by manipulating the qubits with fixed sequence of quantum logic gates, and is the sequence of gates that form quantum algorithms. Governed by the rules of quantum mechanics, quantum computers execute problems using quantum effects such as non-locality, superposition, entanglement, and interference. Unlike the algorithms in classical computers, understanding quantum algorithms and the state of registers require our familiarity with the bracket or Dirac notation of vectors. For a given vector v, the entries of the row vector bra v are the complex conjugate forms of the entries of the column vector ket v, and the inner product of these two vectors forms what is known as the Hilbert space. A qubit is represented using any two orthonormal basis vectors, but usually by the computational basis ket0 and ket1. In quantum computing, a register of n qubits is in a superposition of 2 raised to n possible bit strings, which are represented using n bits when collapsed. Therefore, a 2-qubit register would be in a superposition of 4 possible bit strings formed by tensor products of the single qubit states, and a 3-qubit register. It is believed that 300 perfectly entangled qubits in superposition could map all the information in the universe starting from the Big Bang. Now we're left only with the idea of quantum gates to build our own quantum circuit. A quantum gate is any operation that changes the state of a qubit. Physically, it's done by applying carefully calibrated microwave pulses. Mathematically, these gates are represented using transformation matrices. One of the most common single qubit quantum gates is the Hadamard gate, often known as fair coin flip. Many algorithms begin by applying this gate to each qubit, as it prepares an equal superposition of all computational bases. The other common single qubit quantum gates are the 3 Pauli gates. The Pauli X gate switches the amplitude of the ket0 and ket1 bases. It rotates the vector along the x-axis. The Pauli Y gate rotates the vector along the y-axis. The Pauli Z gate negates the amplitude of ket1 while leaving the amplitude of ket0 the same. The other uncommon single qubit gates are the S gate, T gate, and the phase shift gate. Quantum gates that change the value of a qubit based on the other qubit values are called multi-qubit gates. The controlled NOT gate does nothing to the target qubit when the qubit is 0. Otherwise, it flips it. And the control U gate is its generalization for any unitary operator U. By implementing these gates into the qubits, different algorithms have been introduced since then. The first one is prime factorizing algorithm. This algorithm was first introduced by Peter Shor. With the big O notation explained before, Shor's algorithm is exponentially faster than the best known classical factoring algorithm. The second one is database search algorithm, which was introduced by Lovegrover. The algorithm performs a search over unordered data in a quadratic speedup. Based on the complexity of certain problems, in the near future, quantum computers will help us solve intractable problems. At about 50 qubits, many say a quantum computer could achieve quantum supremacy, said the American theoretical physicist John Preskill. And a couple of weeks ago, Google claimed to have achieved quantum supremacy.
From now on, I'm going to talk about application of quantum computing in the field of chemistry. Quantum computing and quantum information processing technology have attracted attention in recently emerging fields. Among many important issues in science, solving Schrödinger's equation and atoms and molecules is one of the ultimate goals in chemistry. The one enterprise that has made chemical breakthrough using quantum computing is IBM, which is one of the most powerful companies leading the area of quantum computing. IBM scientists simulated the bonding in H2, LiH, and BH2 molecules using a quantum computer. Also, if quantum computing evolved to be better and better, so that we can solve classically intractable chemistry problems, it'll enable us to make design of new materials, medicines, catalysts, and high-temperature superconductors. Next, I want to deal with the topic obstacles. The first one is decoherence. The decoherence theory is reverting a quantum system back to classical through interactions with the environment which decay and eliminate quantum behavior of particles. Superposition for subatomic particles is like balancing a coin. Any small movement, vibration, or even sound can affect the coin from being in a neutral state to collapsing on either heads or tails. The second one is error correction. The quantum computing system, it needs to have full error correction and prove itself fault tolerant. IBM Molecular Energy Calculator consists of 7 qubits, and Google AI Quantum Computer uses 53 qubits with flat rectangular shape. They are also not perfect now, so much larger quantum computing system requires the astonishing ability to correct errors. In spite of many obstacles to quantum computing, but we can develop much better quantum computers. It marks just the first of many steps necessary to develop practical quantum computers. You take one step at a time and you get to the top of Mountain Everest. Leader, University of Southern California says, "This is not the top of Mountain Everest, but it's clearly crossing the pretty big peak along the way." That's all we want to discuss. Thank you for watching our video.